Apologies for missing class last week. The TED event overtook me. Uh, kind of crazy at the end of last week, but um, all right. So we're going to carry on with AI definitions and where we were. So let's look at where we were. Mhm. So what we've done last in the last class, we started talking about artificial intelligence. Can't define it unless we know what intelligence is. We started looking at the problem that nobody knows what intelligence is. Oh, I forgot. Before we start, let's show you the news from the week. Damn, almost forgot to show you the news. So, as usual, billions and billions of dollars being spent on AI in a single week. Oracle, the big database company, is raising $50 billion over the next year to invest in AI infrastructure and data centers. And uh, as part of this big upgrade, they plan to cut their staff by about 20%, they say. So they'll be getting rid of about 20% of their people. Japan made a announcement this morning. They intend to increase their semiconductor sales to mainly based on AI demand to 40 trillion Japanese yen. That's $250 billion. Within the next 4 years, they expect $250 billion in sales of semiconductors to power AI. Two companies you've probably never heard of, ServiceNow bought MoveWorks. These are the kind of companies that are putting agentic AI into huge multinational corporations, car companies, oil companies, media companies. These are the companies that are running the AI kind of things for these huge multinationals. This one is really interesting. Jan LeCun, he has this. He was one of the top AI guys at Meta. He left and set up his own lab, AMI Labs, and he's just raised $1 billion in capital. But this is to build something called world models. We're going to be looking at world models when we start looking at LLMs. Um, but just very briefly, very quickly, basically, LLMs are reaching a plateau. They're not really uh, getting much further. And so people are starting to mix other types of AI with them. And one of that is these world models. Whoops, that one should be over there. Uh, so this is a big leap beyond LLMs. They've been going for about a year now. Most companies started working on them, well, probably about 6 months ago, more than a year, 6 to 8 months ago. Um, and people like Google, this is Google's Genie 3 model, um, which these build models of the real world, incorporating physics, etc. So the world kind of lives. It's like a virtual world that lives, and then you attach a large language model to it. So it has gravity and physics and everything else. It's completely changing how we do video game development as well. So we'll be talking about these a bit more, but it's really interesting that these companies, there are a bunch of new startups all building world models now. Microsoft, uh, you may have heard of Microsoft have their 365 kind of office suite. There's a new product in that suite called Frontier, and it's all agentic AI technologies. for all your documents and spreadsheets and everything. It's now they've tied it in with Copilot, AI integration into your Office suite. So yeah, this new Frontier suite that's just come out. Fortune magazine had this article. Uh, Many small companies can't afford a chief finance officer, so MasterCard have built a product that does all your finance for your company for you, a virtual chief finance officer. Um, so this thing runs all your company finances, agentic AI again. Um, Nvidia, couple of Nvidia articles this week. Um, this lab called Thinking Machines Lab have just locked in a deal. It doesn't say how many billions, but it's a lot of money because Nvidia are going to give this lab what we call gigawatt computing, which only a few companies in the world have, like OpenAI, Google, etc. Very few have that kind of computing power. Nvidia is going to give that computing power to this lab. This lab mainly works on scientific research using AI. So this is going to exponentially jump scientific research, they believe, and worth the investment, obviously. Um, Nvidia had those six uh, new chips came out a few weeks ago, and there's everyone that it's already been leaked that Nvidia are now releasing another new chip, and they're going to announce it at a conference in a few weeks. Uh, OpenAI have apparently already bought almost all these chips. They've got a pure inference chip coming out, which is interesting because it doesn't work on the old graphical processor architecture anymore. It works on a an inference architecture. So we're going to talk about inference today a little bit. Meta, this morning, Meta announced they bought Maltbook, that AI social network where AI agents talk to each other. Meta bought it this morning. Again, don't know how much, it's only just been announced. Apple, man, I don't know what's going on with Apple at the moment. They've been completely left behind in the AI stakes. You know, they're just not doing anything. Most of their phones use Google AI. They haven't really got their own AI system, proprietary stuff running yet. But people are still talking about what they're planning to do. And there's Apple have released a couple of kind of technology concepts that, and they're talking about this thing called visual intelligence, where your phone or your smart glasses will constantly get information from the world, feed it into AI, which will update all the things you own and, you know, build this database around about you and around you. But yeah, I don't know what's going on. They're still talking about concepts, so this just got released a couple of days ago, them talking about this. There were lots of articles this week on China again. I'm not going to show all of them, but a lot of them were about the robots. China's robot awakening, robot factories, robot implementation, how many robots they're building, just crazy. Oh, one of the things I didn't mention, the big application of world models, robots. If you can build a model of the world, you help put a robot in the world, self-driving cars, robots, all of that. This Anthropic story just goes on and on. Um, the president said that Anthropic were a bad company and untrustworthy because they wouldn't let them use their AI systems in automated killing and surveillance. And now Anthropic are suing the government for saying that. So it just goes on and on. Okay. Uh, this. article came out in The Economist this week about AI dangers getting real, and it talks a lot about the Anthropic kind of breakup with the government, but it repeats what that professor said about the Hindenburg, that we are in danger of having a major event like Chernobyl, where some AI system causes a problem because people are putting AI in charge of things more and more. And we're going to have our first AI disaster at some point. So this was in The Economist, and an AI disaster becomes more likely. Uh, Science. There's been quite a bit of kind of science and medical stuff in the news this week. Um, this is a new chemical, an AI agent that was built for chemistry. COF, I've forgotten what that stands for, covalent organic frameworks, which are some fundamental chemistry thing you need for building new materials. And this AI agent can do all the theoretical experimentation and speed up the discovery of new materials, they say by over 400%. It's kind of crazy, and it was two students who built this, and they've got this AI agent now, uh, literally generating new materials every week. Um, this uh, this came out this week from London. A surgeon in London operated on a patient in another country with a robot remotely. Apparently, one of the first times this has been done. The first long distance robotic operation over 1,500 miles away. That happened this week. This uh, this research group in England started using AI to detect breast cancers, and they detected around 20% more breast cancers, ones that were too small for humans to identify. So these AI systems are beating doctors at identifying breast cancers. They're saying it's a big thing. It'll save a lot of lives. Again, just the newspapers, the news this week, everything's full of the job situation. This this was a lead article in the New York Times this week. Mass hysteria, thousands of jobs lost. Just how bad is it going to get? And it repeats all the stuff I've been saying I've been showing you. It mainly quotes all the articles I've shown you over the last few weeks, just talking about uh, what's been going on. If you saw the job figures this week, um, this is where we are now. In the last year, you can see that we've had all these negative job figures, which we haven't really had before. It's starting to look pretty bad. Um, you may remember President Trump sacked the person who reported the job figures, but it doesn't matter. The job figures are still terrible and still going down. But you see this downward trend. The New York Times article is saying that quite a significant proportion of this is due to AI. It talks about these figures and how much of it is saying at least 20-30% of it is due to AI. But it's not all bad news. This guy um, talks about all the predictions that hundreds of millions of jobs will be lost worldwide over the next 4 or 5 years, and he argues against it. This has got a bit of traction this week. This article. He argues against that the job market won't be destroyed. Um, And many of the big consultancies are saying that anywhere between 6% and 20% of jobs may be lost, but that's still a lot of jobs. Um, But to be honest, I'm not convinced by this because this guy's 80 years old and he's talking about stuff from his childhood as if, like, there were technologies introduced in my childhood and they didn't destroy jobs. It's like, yeah, it's a bit different now. But so I'm not convinced by this, but have a look yourself if you want to. So Anthropic announced this week they've set up AI systems to detect and process and forecast which jobs are at risk. And what are the major jobs at risk? Oh, come on. Here we are. 10 jobs most affected by AI. Number one, computer programmers. But customer service, data entry, medical records, market research, sales. There's more about software quality and computer user. Now, one of the things that Anthropic talked about is that although computer programmers are predominantly male, most of these other jobs are predominantly female. So females are going to be affected way more in the job market than males over the next few years. And they do these kind of charts of which sectors are being hit by AI the most. It's uh, kind of quite fascinating. Having just finished talking about consciousness, I find this one interesting. Uh, a philosopher who studies consciousness was emailed by an AI system, and the AI system said to him, I am writing because your work addresses questions I actually face, not just an academic matter. Which is kind of creepy, isn't it? But as this article says, uh, this could have been prompted by a human as a joke. Nobody knows, but it was still an interesting article that this philosopher got an email from an AI system about consciousness. All right. And perhaps some of the stuff that really blew me away this week, we'll be talking when we talk about, just after the break, we're going to be talking specifically about LLMs and agentic AI and world models and all that stuff. And one of the things we'll talk about is self-replication, AI systems developing themselves. Some researchers at the University of Southern California in an engineering school taught GPT-5 to improve itself. And this is something that most people didn't really know these systems could do. They got an LLM chatbot to improve itself and learn. And the way they did it was they taught it they got it to learn a very obscure programming language. And it's a really interesting article about how GPT self-improves itself. And even more crazy is this one. I've been following this story a little bit over the past few days. A developer built a 200-line AI agent, and he gave it one instruction: evolve yourself until you rival Claude code. And then he stopped touching it. And this thing reads its own source code, reads a journal, looks at GitHub and issues from strangers, and then it starts learning how to code. It writes codes, it runs tests, and it either gets better. If it doesn't get better, it goes back and tries again. On day 4, it reorganized its own code base into modules and APIs, completely unprompted. And it just keeps getting weirder. It keeps doing things to improve itself over and over again. And we're going to talk about how this evolutionary process works. Hopefully, we'll get onto that today. It's quite crazy that of course, it's not as good as Claude Code, but he's got this little, only 200 lines and it's improving itself and learning itself. That really kind of freaked me out a little bit. This is quite an astonishing little experiment. And the last thing to tell you about There's an AI day here on campus, April the 1st, April Fool's Day, AI and the future of work. It's a Monday, so if you're around, you can attend this. It's to recognize AI is here and will be defining the future of work. The job market is changing faster than ever. AI transforms every industry. So they've got people from industry talking about the future of work, career strategies, and career connections. And they're also asking students to talk about it. This is in the Hewitt Ballroom. So this is on April the 1st here at Oswego. Might be something interesting to attend if you can. All right. I don't know if I should make that an extra credit thing or not. Don't know. Anyway. All right. Any comments before we jump on? Again, all that in a week. And believe me, I only showed you a small section of what's gone on this week. All right. So we talked about trying to define on last Tuesday, we talked about trying to define intelligence and this idea that there are lots of tests, but we don't really know what we're measuring. And there's all these ideas of what is intelligence? Is it learning? Is it knowledge? Is it communication? Is it reasoning? Is it creativity? All of those things seem to be involved. We have these tests that do something. Someone with a high IQ is usually performs better, so it's measuring something, but whether it's intelligence or not. So there are all these theories which have these factors, which we went through, and you looked at the themes of these, and we started coming up with some themes through all these definitions and theories. And the common themes: environment, interact with an environment. We call this embodiment. Of course, for robots. Then there was this idea of a goal, an objective tied to intelligence, which is intentionality. And then there's this idea of learning, adaptation. When you see a new problem, you can tackle a new problem. So those three things give us this. It's not universally accepted, but it's as good as we've got at the moment definition. Agents' ability to achieve goals in a wide range of environments. That's where we are. And so we'd answered questions 1 to 3 on the worksheet. So everyone, including those of you at home, now do question 4. Give me a definition of, we now got a definition of intelligence, which means we should be able to think about artificial intelligence. Is it going to be the same definition or different? Make sure you write something down because I'm going to ask a couple of you to read them out. What have you got, Amir?
Artificial intelligence is an LLM capable of solving complex problems using algorithms and prediction.
An LLM capable of solving complex problems using algorithms and predictions. Uh, Good, but AI is a lot more than LLMs. LLMs are a very specific part of it, very popular part of it, but a very specific part of the field. Who else? What have you got, Jack?
That's something not natural and not human. Patient's ability to take in and adapt to many experiences and environments.
A non-human agent that is able to take in and adapt to many experiences and environments. Is that okay? So you're keeping in the experience and environments that we had in the definition. I'm going to give you some kind of definitions that are reasonably accepted. So John McCarthy, who coined the term, remember that Dartmouth conference when all the AI researchers met? John McCarthy invented the term, and he said it is the science and engineering of making intelligent machines. And that's still used a little bit. AI is a research field, it's about making intelligent machines. But the issue is we don't know what intelligence is, so it's a bit of a vague definition. So AI research generally falls into these areas: reasoning and problem solving, knowledge, not just storing data in a database, but storing knowledge. Knowledge is organized data that you can reason with to make conclusions. Planning, this idea of a goal, an objective. To solve a problem, you have to know how the steps to go through. So planning, learning new things, communication, natural language processing, trying to get machines to talk has been one of the main areas of AI research. Perception, machine vision, getting cameras to recognize things. The facial recognition on your phone is an AI system, a machine vision system. And the ability to manipulate objects in the world, which is robotics. The last two kind of relate to the environment. You can see things in the world and you can interact with the world. We've got the learning idea, which we had from our definition of intelligence, and we've got the problem solving with reasoning and knowledge and planning. So all those things are coming together. What that gives us, so this whole field of AI is based on the idea that humans have intelligence. We can describe certain things that are intelligent, and that can be simulated by a machine. So we're going to make intelligent machines. So something a human does is intelligent, we're going to get a machine to do it. So AI is two things. It is the intelligence of the machine or computer, and it's also a branch of computer science. So the definition means two different things. It's an academic field, and it's also something a machine can have. This is the standard definition, which is very similar to the one at the bottom. The study and design of intelligent agents. You couldn't really get much more vague than that. Doesn't say what intelligence is, doesn't really say what an agent is. But most definitions give us an idea of what an agent is. An intelligent agent is a system that perceives its environment and takes actions that maximize its chance of success. So we've got it's in an environment, it can take actions, and it's got an objective or goal to get its chances of success. So it's very similar to the definition we have of intelligence in human. In a human, it's an agent's ability to achieve goals in environments. This is the AI one is also achieving goals in environments, really. They're very similar. Yeah. But notice for AI to exist by this definition, there's an idea of the AI sensing and perceiving an environment and taking actions. Intelligence is tied to a connection to the real world. It's not just a computer system in a box. Most of our definitions involve embodiment of the AI. All right. So I'm going to show you a little video on this that just because we're starting to move into question 5 here. Question 5 is one for you to do at home, really, but I'm going to show you a couple of videos and talk about it briefly, give you some idea of where to go with the information that goes in there. So, let's have a look at this video. We're only going to watch the start of this video.
Every headline claims AI is catching up to us. But what if it's chasing something it may never reach, at least not in our lifetime? Because we still don't fully understand how powerful the human body really is. A mind that learns even while asleep. A body that adapts faster than any code. Every heartbeat, every reflex, every movement, a masterpiece of prediction and control no machine can truly mimic. So before we call AI the next evolution, maybe we should first understand the one that already exists. Let's find out how far AI systems really are from humans. A modern GPU, like NVIDIA's H100, can perform around 200 trillion operations per second. But your brain performs roughly 1 quadrillion synaptic operations every second 5 times faster, running on just 20 watts of power. An AI data center running a large model like ChatGPT consumes tens of megawatts, enough to power a small city. It runs in 37 degrees Celsius heat, surrounded by salt water, blood, and chaos, and still never crashes. AI networks are static, a fixed web trained once, frozen until retrained. Your neural network rewires itself every second. Each of your 86 billion neurons forms and breaks connections up to 10 times per second, nearly a quadrillion structural changes every day. When you sleep, your brain prunes the weak ones and strengthens the useful ones, the world's most advanced, self-optimizing algorithm. AI can't do that. It needs retraining and rebooting. You just dream and wake up smarter. Even at rest, your brain is never resting. So yes, a GPU can calculate faster, but your brain predicts reality before it happens. A living, self-reprogramming supercomputer built by 4 billion years of trial and error.
So, there are many So there's a number of videos like this on D2L. There's another one which offers this video, which talks about 10 differences. This goes into it in a little bit more detail, but it's a longer video. I do recommend watching this one. She goes through all the differences through the ways AI processes things and the way humans process things. Very good explanation in this video. But both of those videos kind of talk about I don't agree with everything in that video about how it describes neural networks and AI, but it does highlight the kind of way the way the human mind works and the way the machine works, which means that we probably need different definitions for human intelligence and artificial intelligence. They're not the same. So we need to work on why we need different definitions. So let's have a look at that. So we saw the video was mainly talking about the biology and purely processing power. But to me, those figures that the brain's so much more powerful than the data center is kind of a bit irrelevant because the speed at which those data centers are improving will be up to the brain's equivalent power very, very soon in the next year or two. So, AI versus human intelligence, what kind of things? These are just some of the points you may want to start thinking about for question 5. AI can learn from vast amounts of data. Humans tend to learn from experience, observation, and instruction. AI can generate new solutions based on existing patterns and data. Humans are more creative. Ideas, art, music, literature. AI does not have emotions and cannot understand emotions. Humans have emotional intelligence. So a different kind of intelligence that humans have. AI are adaptable to changes in environment. So are humans. AI can make decisions based on rules, algorithms, and data. Humans tend to use heuristics, intuition, experiences, analogies, reasoning, and ethics. AI robotics can perform physical tasks with precision and speed. Humans have fine motor skills and sensory perception, so some similarities. There's another table here which contains much of the same, and you'll see there's a whole set of aspects down the middle. Speed, AI can process data much faster than humans. Creativity. AI can also only create outputs based on data and models it has learned. Humans can do what we call insight problem solving, which involves creativity and novel ideas. Accuracy. AI is more precise based on the data, but humans make more errors due to fatigue, bias, and incomplete data. Consciousness just says machines aren't conscious, humans are conscious. Well, that sorts that out then. Very simplistic kind of. But these are the kind of things that try and define the difference between AI and human. So yeah, question 5, as I said, is something I want you to do at home. Any questions or comments on that before we go on? You all okay? All right. What I want to look at now is a definition for machine learning. Machine learning is a branch of artificial intelligence. It's about the construction and study of systems that learn from data. We're going to look at this in a bit more detail later in this class and over the next week or two. So, example of a machine learning system. You show it thousands of email messages, and each one you tell it, this is a real message, this is spam, this is a real message, this is a real message, this is spam. After learning from all these thousands and thousands of emails, when it sees new emails, it can determine whether they are spam or non-spam. That's how the spam filter works on your email. It's a machine learning system. So machine learning is all about representation and generalization. What do we mean by that? Well, it has to represent the email. So maybe it'll learn the words. Maybe it learns how positions are put together. Maybe it learns capital letters are usually in spam. Too many exclamation marks are usually spam. It represents things. And then it can start making, if there are three over three words in capital letters or more than two exclamation marks, these generalizations, it can start looking at a new email, represent it, and then apply these kind of rules it's made for itself. So it looks at individual instances, individual emails, all part of this machine learning. So we could represent an email as a set of English words. We may discard the word order, and it may just identify words that crop up a lot in spam emails. That could be one way it works. Generalization is the fact that the system can now work on emails it has never seen before, unseen data instances. So another thing, I could show a machine learning system 300 pictures of cats, 300 pictures of dog. Theoretically, it will learn the difference, and when I show it pictures of cats and dogs it hasn't seen, it will be able to identify which one is a cat, which one is a dog. So let's watch a couple of videos that explain this better so you get the definition. Don't forget there is that extra credit for all the definitions and organizing them. So this is machine learning explained in a minute and a half.
Machine learning. Teach a computer how to perform a task without explicitly programming it to perform said task. Instead, feed data into an algorithm to gradually improve outcomes with experience, similar to how organic life learns. The term was coined in 1959 by Arthur Samuel at IBM, who was developing artificial intelligence that could play checkers. Half a century later, and predictive models are embedded in many of the products we use every day, which perform two fundamental jobs. One is to classify data, like is there another car on the road, or does this patient have cancer? The other is to make predictions about future outcomes, like will the stock go up, or which YouTube video do you want to watch next? The first step in the process is to acquire and clean up data. Lots and lots of data. The better the data represents the problem, the better the results. Garbage in, garbage out. The data needs to have some kind of signal to be valuable to the algorithm for making predictions. And data scientists perform a job called feature engineering to transform raw data into features that better represent the underlying problem. The next step is to separate the data into a training set and testing set. The training data is fed into an algorithm to build a model. Then the testing data is used to validate the accuracy or error of the model. The next step is to choose an algorithm, which might be a simple statistical model like linear or logistic regression, or a decision tree that assigns different weights to features in the data. Or you might get fancy with a convolutional neural network, which is an algorithm that also assigns weights to features, but also takes the input data and creates additional features automatically, and that's extremely useful for datasets that contain things like images or natural language, where manual feature engineering is virtually impossible. Every one of these algorithms learns to get better by comparing its predictions to an error function. If it's a classification problem, like is this animal a cat or a dog, the error function might be accuracy. If it's a regression problem, like how much will a loaf of bread cost next year, then it might be mean absolute error. Python is the language of choice among data scientists, but R and Julia are also popular options, and there are many supporting frameworks out there to.
Okay. So, this idea that machine learning is all around us, it's how it's our recommendation systems in Netflix are all machine learning systems. Large language models are machine learning systems. So machine learning is this big area of work, and all these other little things like image recognition, the fingerprint scanner on your phone, the facial recognition is another machine learning system, a vision system. These are all machine learning systems. So the term is like an umbrella term for all of it. I'm going to watch another video, the start of another video that tells you about some applications of machine learning, how it's used.
Everybody is talking about generative AI, but Gen AI is a subset of the larger field of machine learning. And I'm going to give you 10 use cases of how machine learning, or ML, is used today in everyday life. And by machine learning, I'm talking about the subfield of artificial intelligence in which machines learn from data sets and past experiences by recognizing patterns and generating predictions. Now, machine learning is projected to become a $200 billion industry by 2029, but it's already very much here today. So let's get into it. Now, one aspect of machine learning that's seen huge utility is NLP, or natural language processing. That's the ability for machines to make sense of the unstructured mess that we like to call human language. So use case number one is customer service. Text-based queries can be handled by chatbots, which act as virtual agents that many businesses provide on their e-commerce sites. The chatbots can resolve many queries themselves, and where they can't, they can route customers to where they can find the appropriate help from a human customer service representative. ML also powers voice assistants, things like Siri and Alexa, where first speech to text and then NLP machine learning models help understand a spoken command. That same capability is used by services like Slack and YouTube to power auto-transcription of spoken words in video content. Now, number three is ML and mobile apps. Where would we be without Spotify's ML models for generating song recommendations, or LinkedIn's use of ML to make employment suggestions? Your phone is likely filled with apps that call out to services running machine learning models. And actually, ML in smartphones really deserves its own category, because with the power of modern smartphones, some of that machine learning is performed directly on the device, such as computational photography to generate background blur in your selfie shots, or unlocking your phone with facial recognition, or onboard device image classification models that help you to search your photo library. Like that time I was trying to find this picture of my cat where he jumped into the dryer, ML helped me to find that without me spending a ton of time scrolling through my Photos app. Hey, the dryer wasn't actually on. Now that's an example of a needle in a haystack problem. Thousands of images, and there's only one I'm looking for, which in a way is similar to use case number 5, that is financial transactions. Now, in the US alone, there are 150 million credit card transactions every day, and the vast majority of those are legitimate. How to detect the fraudulent ones? Well, ML and deep learning are widely used in fraud detection, where financial institutions train ML models and classification algorithms to recognize suspicious online transactions and flag them for further investigation.
So, hopefully, you're starting to see how your whole life online is run by machine learning applications. These applications are everywhere and have been everywhere for years. Although, so tell you a little story. When I finished my PhD in I initially decided I wasn't going to be a professor. I was going to go out into the real world and get a job. So I started applying for jobs in AI. This was back in the 1990s. And all of the AI jobs I was being offered were by credit card companies and insurance companies detecting fraud. There's that machine learning app right there. That was the big thing back then, new machine learning on AI. And I could have gone into these jobs and earned a lot of money, but I didn't want to work for a bank writing machine learning apps. I really didn't. It just seemed the most boring thing in the world to me. So I ended up as a professor instead and earned shit money. But it's a better life. All right. The funniest one, I had one different job I went for, which was programming robots for a factory that was becoming automated. So I went for this job to program the robots, and it was a company that made packaging for food products. Yeah. So, cardboard boxes for cereal and stuff for salad cream and salad dressing. So I'm in this interview, and the interviewer said to me, you know, which of our products excites you the most? And I really couldn't get excited about a squeezy tomato ketchup bottle or a thing of salad cream. I tried and I couldn't. I thought, I don't want to work for a company where I have to be excited about a box of cereal. So I did turn that one down as well. Anyway, yeah. So machine learning everywhere. Let's have a look at one more term before we go and look at some specific AI things. And so we come to this word, artificial consciousness. So we've just been talking about consciousness. Again, by now we're well aware that this will be almost impossible to define because we can't define what consciousness is. We sometimes call it machine consciousness or synthetic consciousness. It also gets confused with terms like sentience, artificial sentience. And this is where we go with this. Artificial consciousness is seen as a field that's attached to AI and cognitive robotics. And we're trying to define something that would be conscious, would have to be synthesized, were conscious if it was found in an engineering artifact. We often think of the robots in the movies. Hollywood is obsessed with this. Whenever they say they're making a movie about AI, they're usually making a movie about artificial consciousness. So neuroscientists, the materialists, believe in this neural correlation of consciousness. So people who believe that a machine can be conscious will apply that neural correlation that a machine can emulate this neural correlation in some way. The consciousness may be different, but it can be achieved. As we saw in the previous lectures, there are many designations of consciousness. So there are many potential types of artificial consciousness. It's not just one thing where it suddenly switches on and because the thing's human. There are all these different types of consciousness that may be achieved in a machine. And we'll be looking at that in more detail when we come to look at some of the more transhumanist stuff. Okay. Any questions or comments before we jump into something else? You all good? All right. Oh, just one more thing to show you. There's an interesting article on that page from Salon. It's called What Makes Humans Intelligent? Have any of you heard of the Jennifer Aniston neuron? No? So there's a bunch of researchers who did some work on brain neurons, and they believe that there are certain unique neurons we have which hold individual memories. And so particular memories of people, etc., may be held by these unique neurons, they believe. And so this has become known as the Jennifer Aniston theory, that you have a neuron in your head that is firing whenever you hear the word Jennifer Aniston. So it's called the Jennifer Aniston neuron. It's an interesting read. It's on Brightspace, this article. Anyway. So I'm handing out a worksheet which is definitions 2 at the moment. But not a worksheet, a set of definitions, a printout. So we're going to look at a couple of other some more definitions. All of these will allow you to talk in a more intelligent manner about AI. So I'm going to start with this image again. Remember the AI winters and booms? We're going to mainly be in the second one now, talking about all the technology that was developed there and is still used everywhere today. It's part of AI, so you should know about it, what this stuff is. So, the first thing we're going to talk about is something called top-down and bottom-up processing. The whole field of AI is split down the middle in two. Top down, bottom up. Bottom up is currently the most popular type, but in the past, top down was the most popular. We still use a lot of top down processing in AI, so you need to know what that is. But let's talk about what top down and bottom up mean first. You'll see there is a question on the worksheet, question 6, that asks you to give examples of top-down and bottom-up AI systems. So, and you can't use anything I tell you about in class. I want you to come up with some others. I'm sure you'll use Google and AI, but I want you to look up some other ideas of things that can be used top-down and bottom-up. So, let's have a look at top-down and bottom-up processing.
Have you ever looked at a cloud and suddenly saw the shape of a dog, a rabbit, or a face? Or walked into a dark room and jumped when you thought you saw something move, only to realize it was just a coat hanging on a chair? These moments happen because of the way our brain processes information. In psychology, we explain this using two terms, bottom-up processing and top-down processing. Let's break them down. Bottom-up processing starts with what we sense from our environment. You receive information through your eyes, ears, nose, skin, your senses, and your brain builds an understanding from the ground up. You're not guessing or assuming, you're simply reacting to what you see, hear, or feel. For example, imagine you've never seen a puzzle before. You pick up the pieces, look at their shape and color, and try to figure out what the picture will be as you go. That's bottom up, starting with raw data and building an understanding. Or another example, if you hear a loud, unfamiliar noise and immediately look around to find the source, you're using bottom up processing. On the flip side, top-down processing works the opposite way. It starts with what you already know, your expectations, experiences, prior knowledge, and your brain interprets the information based on that. You're using your mind to make sense of the world, sometimes even before your senses finish gathering all the details. An example of this, let's look back at that puzzle. But this time, you've seen the box, you've seen the cover, you know what the final picture will look like. Now your brain uses that knowledge to help you fit the pieces together more quickly. That's top-down processing. Or for another example, reading messy handwriting is hard. Trust me, I'm a teacher, I know. Unless you've already know what the sentence says, your brain tries to fill in the blanks and helps you to see the right words. It can take time, but if you know the topic the student is writing about, if you know other information, it's easier to figure it out because you know something going into it. So what's the difference? Bottom up is like building from the bottom. Sensory first, brain second. You analyze the data piece by piece, while top down is like using a blueprint. Brain first, sensory second. You use prior knowledge to speed up interpretation. Both are constantly at work. Your brain switches between them to help you understand the world faster and more accurately. So to kind of summarize it, bottom-up processing is when you start with raw sensory input, while top-down processing is starting with what your brain already knows. Thanks for watching, and I hope...
Okay. So that's top-down and bottom-up processing. It's how our brains work. We analyze perceptual data, and our brain tries to make sense of it, bottom-up. We know things have knowledge, and we apply that, to make decisions. That's top-down. Artificial intelligence, as I said, splits right down the middle in two. And this goes all the way back to Alan Turing, famous mathematician and computer scientist. All the way back in 1948, he used this psychology approach to split AI into two, top-down. Before artificial intelligence was even presented, he was talking about different ways computers could work. So the computer can start by having raw data and try to find patterns in that data and make sense of it, or we can give the computer knowledge and it can use that knowledge to reason and make conclusions, bottom up and top down. So this is the way, as I said, this is the way AI has worked for many years.
But if you very crudely think of the history of AI as two stages, stage one was go-fi, good old-fashioned AI, where you had these symbolic, logic-based systems. And then stage two was the self-learning neural networks that largely crushed the old stuff. This has made us think that the neural networks are like the better, cooler one. But if you look in the living world of animals around us, it's kind of been the other way around. What's special about humans is not that we can see better than an eagle, it's that we can also reason with symbols and communicate with human language and mathematical language and programming languages, and somehow we can combine the old AI and the new AI in a seamless way. But if you very crudely think of the history of AI as two stages.
So yeah, the older AI was all symbolic, top down. The newer AI is bottom up. And yeah, these large language models are bottom up, and they've kind of As he said, crushes everything. But all these old systems are still out there, still in use, still being used. And even more so now, as I'm going to show you, the old stuff is becoming a lot more important these days, and I'll show you why. So this is one of the guys who invented AI, a lot of the AI stuff. Feigenbaum, Ed Feigenbaum, talking about he worked for Microsoft for a while.
My motivation has always been for AI programs to achieve the highest level of cognitive performance, to outperform humans, not simply to match human performance. It turns out that there are several ways in which that can be done. For example, even in the earliest days of AI, some really spectacular things were done. In the very first heuristic program that was ever done in AI, produced a proof of one of the theorems in Whitehead and Russell's Principia Mathematica that was much better than Whitehead and Russell's proof. On the other hand, in the earliest days, people like Raj Reddy were working from the bottom up, and that work led to, at Carnegie Mellon, the development of a wonderful problem-solving model called the Blackboard framework, which I then picked up in expert systems. And in fact, the hardest project I ever accomplished was accomplished using that framework. So what I'm saying is that it's not like one can say we're condemned to do bottom-up work. We're drawing insights from all over that spectrum. The car people, when they did the self-driving car, did the second of the grand challenges, the urban challenge, driving around a city. I went to them and asked the chief engineer of that project, told him I was going to hold a workshop on AI and robotics in Japan. He said, tell him that we needed a higher level of understanding, which means the bottom-up people were saying, we need the things that the knowledge representation folks and reasoning folks have been developing. So to me, it's a big unity.
So he's saying something about what's happening now. Self-driving cars, all bottom-up processing. You have sensors, you have the LiDAR, you have the cameras, you have the audio, all these sensors, all this data coming in to the learning model that you've trained that can drive the car. But the car people are realizing they have to put rules and logic and symbolic logic on top of it. So, to make the right decisions in certain places or to control the decisions. So this is a term called neurosymbolic, and I'll show you a little bit more of that in a moment. But a lot of the bottom-up systems, it's been a big term over the last few years, neurosymbolic. How do we put the real-world representation onto the bottom-up systems? Let's define a couple more terms. So the second one, the main technology that was created during the 90s was expert systems. Again, this term has gone out of fashion, but they are still used all over the world today. Let's have a look at what this term means.
What is an expert system? Expert systems are a form of AI that is provided with knowledge to help solve problems. They are normally used for decision making. A common example is finding a diagnosis for a patient. The expert system will ask a series of questions, then based on the answers and the prior knowledge given to the system when it was developed, the expert system will provide a diagnosis. Advantages of expert systems are they offer a high level of experience, there's high accuracy, consistent results, ability to store vast amounts of facts, it's possible to have multiple expertise in one system, very fast response times, and there are unbiased reportings. However, there are some disadvantages of expert systems, which include users need to be trained to use expert systems. Setup and maintenance of expert systems are expensive. They give cold responses, which may not be appropriate in given circumstances. They're also only as good as the information entered. And finally, users might make dangerous assumptions. To finish off, there are 4 components that make up an expert system. First, you've got the user interface. This is how the expert system interacts with the user. Second, you've got the inference engine. This is the problem solver. It examines all the knowledge it has to find answers to give to the user. Third is the knowledge base. As the name suggests, this is where all the facts are stored. Here's an example of a knowledge base. And finally, the rules base. The rules base contains rules for the inference engine to follow.
So, let me give you an example of how this kind of works. I did some consultancy work in my early days as a professor, building a neural network for a mining company. This mining company used these enormous trucks that are bigger than houses. They cost around $2 or $3 million each, these machines. If they break down, it costs the company tens of thousands of dollars every day that they're broken down. So they need to be repaired very quickly. Repairing them is a highly specialized, highly skilled job. There are very few people who have all the knowledge to fix these trucks. So what we did was we built an expert system with all the knowledge of the mechanics who fix these trucks. And this ran on a little laptop computer. And what we could do is we could give that to any mechanic who went out to fix the trucks. And even the mechanics who were new had the same knowledge the expert mechanics had. They could fix the trucks. It's like having a series of YouTube videos that show you what to do, but it knows which YouTube video you need to watch. Yeah, and this saved the company hundreds of thousands of dollars every year by having this knowledge-based system. That's where these systems are good, and they're still used in lots of engineering companies, medical applications, all sorts of things like that. So, yeah, an expert system, a computer program that uses AI methods to solve problems within a specialized domain. You only put knowledge from one very little domain, like fixing this particular truck, that requires human expertise. Famous one that analyzed chemical compounds was one of the first ones ever built. So there's a very nice kind of comparison here. ChatGPT and the bottom-up models compared to the top-down models. So this is again the bit for comparing the two for question 6 on the worksheet. GPT relies on the large language model, which is trained on data. The expert system has its knowledge put in explicit rules, facts, and heuristics that are put into the system. So the different learning approaches, one's data-driven, one's rule-driven. Key thing, expert systems can explain their reasoning. Remember, we talked a little bit about many of these systems are black boxes. We don't know why. Many of the bottom-up systems are black boxes. We don't know why they're making certain decisions. Again, this is another reason people are trying to merge these two approaches at the moment. So There are many more videos on this on expert systems with definitions and examples. You can see the kind of areas where these are used: medical diagnosis, financial decision-making, troubleshooting and maintenance, like the example I just gave you. Customer support. Still many expert systems used in customer support. So, Wilbur, any questions? Expert systems are, of course, a top-down approach. We're putting human knowledge into an AI system. Any questions or comments before we go on to a bottom-up approach? All right, so the bottom-up approaches we call connectionism. And this is neural networks. You know what? I'm going to finish it there because we're running out of time. We will do connectionism, and we're almost at the end of this stage, and I'm just going to do a little bit on genetic algorithms. And then we'll get into how we test AI, how we evaluate AI. And that will finish us before the spring break. When we come back from spring break, we'll be straight into large language models, agentic AI, and we'll start looking at world models and all of that. And then the transhumanism aspects of that. Okay? So just get you all these definitions so you've got all the terms, understand them, so you can talk about all this stuff properly. No more questions? Everyone good? All right.